Okay, so our next lesson, Lesson 8, Sequencing Reflections and Translations. So in the previous lesson we were introduced to sequences of translations. It was clear that when a figure is translated along a vector, we could undo the move by translating along the same vector, but in the opposite direction, creating an inverse transformation. Not all transformations can be undone, though. For that reason, we will investigate sequences of reflections. So let there be a reflection across line L. What would undo this action? What is the inverse of this transformation? A reflection is always its own inverse. So consider the picture of a reflection across a vertical line L. Notice how P is being reflected to P prime, Q is equal to Q prime, A is being reflected across to the right to A prime, and of course the L reflected along itself is equal to L prime. Trace this picture of a line L and the points P, A, and Q as shown. Create a reflection across the line L followed by another reflection across the line L. So using your transparency, take the last picture that we did, or that I showed you, and just keep flipping your transparency over. What do you notice happening to P, A, and Q? So is a transformation corresponding to flipping the transparency once across L and then flipping it once more across L? Obviously the red figure on the transparency would be right back on top of the original black figure. Everything stays the same. So let us take this opportunity to reason through the preceding fact without a transparency. For a point P not on the line L, what would be the reflection of the point PB? So reflecting it once and then reflecting it again. Well, the picture shows that the reflection of P is P prime, is a point to the left of L, and if we reflect the point P prime across L, clearly we get back to P itself. Thus the reflection of point P is P itself. The same holds true for A. The reflection of point A is A. So for point Q on the line, what would be the reflection of point QB? Well, the lesson on reflection shows us that a point on a line of a reflection is equal to itself, i.e. the reflection of Q is Q. Then the reflection of point Q is also Q. So no matter how many times a point on a line of reflection is reflected, it will be equal to itself. So based on the last two statements, we can say that the reflection of P is P for any point in the plane. Further, the reflection of P followed by the reflection of P is I, where I is denoting the identity transformation. So P stays itself no matter how many times you reflect it. In terms of transparencies, the equation above says that if we flip the transparency, on which we have traced a given figure in red, across the line of reflection, then flipping once more across L brings the red figure to coincide completely with the original figure. The only conclusion is the stated equation. Alright, so on your lesson worksheet, go ahead and do exercises 1 through 3, pausing the video. Try those on your own, and then continue the video to check your answers. Alright, so you should have exercises 1 through 3 done. Here are the answers. So, translating a figure across vector AB, and then translate the image of a figure A along vector BA, is dealing with how to undo a translation. But now if we're talking about reflection, reflecting figure A across line L then reflects figure A across line L again. Can a translation undo the transformation? No. To undo the transformation, you would need to move the image of figure A after the translations back to figure A. The listed translations do not do that. So, again, the difference between translating and reflecting. Translating you can undo by moving in a different direction, but reflection is just, if you reflect again, you end up in the same spot. Does the order in which we sequence rigid motions really matter? Well, consider the reflection followed by a translation. Would a figure be in the same final location if the translation was done first, then followed by the reflection? Let's see. Let there be a reflection across L, and let T be the translation along vector AB, and let E represent the ellipse. So here is our picture. Which transformation happened first? So if you're looking at E, you have a line of reflection and you have this vector AB. We have two red ellipses here. What happened first? Will the image of the ellipse be the same or in the same place if we translate it first and then reflect it? How is this different from this picture? Notice how this looks like a T, and from the original one, this looks like a backwards L. So notice that one is done translation and then reflection, and the other is done reflection then translation. So yes, it does matter the order that you do transformations. So it should be clear that the order in which rigid transformations that are performed matters. In the previous examples, it was observed that the reflection followed by translation of E is not the same as a translation followed by reflection of E. Therefore, a translation followed by a reflection and a reflection followed by a translation are not equal. Let's go ahead and take a look at this video on how these all are related. Okay, so that's what it looks like if you were to do a translation, a rotation, and then a reflection. So now back on your lesson worksheet, go ahead and try exercises 4 through 7, and when you're done, continue the video to check your answers. Okay, you should have exercises 4 through 7 done. Let's go ahead and see how your diagram, check your diagram against the diagram here. And then here is the sample work for question 6 and the answer to 7, no. The translation followed by reflection would not put the figure in a different location. Alright, let's summarize. We know that we can sequence rigid motions, any of the three: translation, rotation, or reflection. We have notation related to sequence of rigid motions, so we know how to denote when we're moving by primes, double primes, triple primes. And we know that a reflection is its own inverse, so to reflect again means to reflect back to its original spot. And we know that the order in which we sequence rigid motion matters. All right, we'll see you in class.